In today's lesson, we are going to be looking at probability and combinations. So similar to when we were dealing with permutations, we made the connection to probability in the end because we can look at the number of possible ways or combinations of trying to find something now and think of, okay, what is the percent chance or what is the probability of getting one of those combinations or getting one of those groups. So it's going to contain similar ideas. We've dealt with probability before, so we've looked at the different scenarios. We have hopefully a general understanding of what probability is. So now let's combine it with combinations. So again, just to recall the general form for probability, P is equal to NA over NS. Basically the number of successful outcomes. Usually it's the part that's involving restrictions. So we have to select a certain number of people, or we have to have so many winning numbers. Usually that's the part that's on top. And NS is the total number of outcomes, or basically what are the number of ways or combinations without restrictions. So just in general, what are we trying to do, and how many ways are there to do that without any restrictions. So for example, to win the grand prize in a fundraising draw, you need to match 7 numbers from 1 to 27 without regard to order. So similar to the Lotto 649, it doesn't matter what order you match those numbers in as long as you select the same 7 numbers. So what is the percent chance of winning the grand prize? Well, let's break it up into the two parts, similar to what we did before with permutations. Right, so we know that the probability is equal to NA over NS. And let's break it up into two parts. NA is going to be the number of successful outcomes. So in this case, winning the grand prize. Well, how many ways are there to win the grand prize? Well, in order to do that, we need to have 7 winning numbers, and we need to choose those same 7 winning numbers. You could then argue that there are then 20 losing numbers, and you're choosing 0 of them. So we've dealt with questions like this before. So we have our winning numbers. There's 7 of them, and we're choosing 7. And then there are 20 losing numbers, and we are choosing 0 of them. On the bottom, for the total number of outcomes, we have to look at, again, what are we doing in general? Well, in this case, we are selecting 7 numbers. So there are 27 numbers, and we're choosing 7 of them. So we bring this all back together to our fraction, and we get, well, 7 choose 7 times 20 choose 0. There's only one way that can occur, divided by 27 choose 7, which is 888,030. So 1 over 888,030, that is the probability of matching 7 numbers without regard to order, or it works out to 0.0001126%. So a very small chance of winning, matching the 7 numbers. B is now saying, what is the percent chance of winning second prize, which involves matching 6 of the 7 winning numbers? So again, similar to what we just did, we're going to break it up into our two parts. Successful outcomes over total number of outcomes. Nice thing is we've already calculated the total number of outcomes. It was 27 choose 7. That's the scenario that we're doing without any restrictions. On the top part, the number of successful outcomes. In this case, a success is matching 6 of the 7 winning numbers. All right, so let's break our 7 numbers, because again, we have to choose 7 numbers, into the two parts. We'll look at the winning numbers first. So there's 7 of them, we're choosing 6. And we're going to multiply that by the losing numbers that we're choosing. So in this case, there's the 20 losing numbers, and we're choosing 1 of them. That's the second component of our group of 7 numbers that we've chosen. So there's the winning numbers part and the losing numbers part. We bring these two pieces back together. We have 140 divided by the 888,030. So that gives us a probability of 0.0158%. So we're almost at a 1% chance of winning, but we're not quite there yet. So the probability of winning 6 or matching 6 of the 7 winning numbers is 0.0158%. What is the probability of not winning for first or second prize? So now here, not winning first or second. So we're looking at two cases that we can't have. So in this case, we might have to use a little bit of the indirect method, or we could look at winning the third place prize, the fourth place, the fifth place, the sixth place. Right? But again, we don't really know what those restrictions are. We're just looking at what is the probability of not winning these two. So because we don't really know the stipulations for winning the other prizes, it's probably easier to use the indirect method. Again, two parts. So let's break it down into the two parts. Successful outcomes and total number of outcomes. Again, because we're in the same scenario, the total number of outcomes is the same thing, 27, choose 7. For the number of successful outcomes, which is not winning, might as well highlight the not, of not winning first or second, we're going to take the total number of possible outcomes and we're going to subtract, so this was the total, we're going to subtract the ways to win first place, which is 1, or first prize, minus the ways to win the second prize, which is 140, and that is going to equal the number of ways of not winning first or second. So this is our total. We minus our first prize, minus our second prize. Now we're going to put it all together. So now we have 887,889 possible ways of not getting first or second. And then we have 888,030, which equals 99.98%. So now that's how you would do it if you were just looking at the other scenarios, or you could, because we have all the other scenarios. Additionally, what you could do, we already know the percents of winning first and second place, or the first and second prize. So you could look at the indirect method only involving probability. Right? So we have 100%, which is the total number, the total probability in general of all events. So 100 minus first place, which is 0.001 rounded, minus second place, or second prize, which we found is 0.0158%. And in the end, this would then work out to the same thing, 99.98%. So you could look at just the percent, since we already went through and did that in A and B. You could look at it individually by making up the number of successful outcomes and the total number of outcomes. So again, different ways to solve. Example 2, a teacher uses a random name generator to select 6 students to present their projects on a given day. In a class of 23 students, 12 are male and 11 are female. What is the probability that an equal number of male and female students will be chosen to present? Well, let's go through and take a look. So the probability that an equal number of male and female students. So that's key, because that's the successful outcome. That's what we're looking for. So again, probability is equal to NA over NS. We'll break it up into our two parts. NS sometimes tends to be a little bit easier because we're looking at this without restrictions. So we usually don't have to look at different components or anything. We're just looking in general. So what are we doing in general? Well, if we look at the scenario, we're selecting 6 students in a class of 23 students. So that's what we're doing in general. So 6 students from 23, no restrictions. 23, choose 6. So that's our total number of possible outcomes. Now for the successful outcomes, we again go to what we're looking for, equal number of male and female students. So in this case, it would have to be 3 males and 3 females. So we have 12 males and we're choosing 3 of them, multiplied by 11 females, choosing 3 of them. We're looking at males and we're looking at the females. Again, it doesn't really matter what order you do it in because you're multiplying. You could put the females first, the males second. It doesn't really matter when you're looking at the group in general. We can now bring it back together, combine these two parts. We do have to find the probability. So we end up with 36,300 divided by total number of possible outcomes, which is 100,947, which works out to roughly 36%. So there's a 36% chance that an equal number of male and female students will be chosen. What is the probability that more female than male students will be chosen? Well, in this case, again, let's go through and break it up into our two parts. Number of successful outcomes, or total number of outcomes, is easiest again to start with first, especially because we've already done a question with this. So it's 23, choose 6, same value as before. Now for the number of successful outcomes, more female than male students. So that means a couple things. That means we have multiple cases, because it doesn't specify how many, it just says more female than male. So if we look at, say, case 1. Case 1, we would look at more female than male, so 4 females, and then 2 males. Again, we're still choosing 6. So we have 11 females, and we're choosing 4 of them, multiplied by 12 males, choosing 2 of them. The next case, we're looking at 5 females and 1 male. Let me just organize this a little bit better. So 11 females choosing 5, multiplied by 12 males choosing 1. The third case, case number 3, we have 6 females and 0 males. That's also a valid case. We have more females than males. So it's 11 choosing 6 multiplied by 12 choosing 0. We don't really need to include that last one if we don't really want to, but it still applies. It sometimes helps because we have to still think about the two components of our group. So because it's case 1 or case 2 or case 3, we are going to be adding these together. So when we bring it all back, case 1 works out to 21,780 plus case 2, which works out to 5,544 plus case 3, which works out to 426, all divided by the total number of ways, which we had previously calculated anyways, 100,947. And when we go through and we calculate this probability, we end up with roughly 27.5%. So there's a 27.5% chance of selecting more females than males when we go through and we randomly choose 6 to present. Example 3, we want to state the probability of the disk ending up in each slot at the bottom of this Plinko board. So we're going to go through and we're going to use Pascal's triangle to help us figure out the different options. Right? Again, we talked about the Plinko board and Pascal's triangle, right? Because it kind of helps us figure out the number of pathways. So the ball drops down here, so there's one pathway to get to this node. Or you could say there's one pathway here, enters down here. There's one pathway to this opening, one pathway to here, and we can continue it down diagonally. Right? Again, the borders tend to be the easiest spots to fill out first. It generally tends to be the same value all the way through. Then in our third row, or technically row 2, there's 3 options in the middle, or sorry, not 3, 2. One from the left, one from the right, and it's 1, 3, 3, 1. And again, we talked about assuming that once we get to here, it just drops straight down. So if we look at the entire bottom row, there's 0, 1, 3, 3, 1, and 0 in terms of ways of the disk ending up at the bottom of the Plinko board. Now again, this is assuming that it doesn't bounce up. It can't bounce over more than one, right? It has to follow these pathways. In reality, is that the case? No. But again, we're making a few assumptions here. So in total, there are 8 ways for their chip to get to the bottom of the board. So that's going to be our NA, or NS, sorry. So I guess I should keep it similar in terms of the color coding. So NS is going to be 8. So now when I look at each scenario, if I want to find out how many ways to get to slot A or spot A or prize A, you could say, probability to get to A is 0 out of 8, or a 0% chance. To get to B, probability of getting to B is 1 out of 8. C is 3 out of 8. D is also 3 out of 8 because there's 3 ways to get to that last spot. E, there is 1 out of 8. And then lastly, put F all the way back up at the top. F, there is 0 out of 8 possible ways, or the probability is 0%. So again, the probability for this one is relatively straightforward, nothing too tricky to find the number of successful outcomes and the total number of outcomes. However, we do have to use Pascal's triangle, or that concept or that application of combinations, to help us figure out the number of ways the board or the disk ends up at the bottom of the board. Final example, you are making a pasta sauce. You have 5 different vegetables to choose from, but haven't decided how many different vegetables to include in the recipe. You can choose anywhere from 2 to 5 different vegetables. What is the probability that you use carrots in the sauce, assuming carrots is one of the 5 vegetables? So there's a lot of information here. Right? So there's a couple different things we probably should highlight. So again, a good rule or a good kind of strategy to follow is to read through your question and then read through it again and highlight anything important. So we're making a pasta sauce. Not really important. Doesn't matter what we're making. We have 5 different vegetables. Okay, that is important. We have 5 different vegetables. We haven't decided how many different vegetables to include, but we can choose anywhere from 2 to 5 different types. So we don't know how many we're actually going to use, but you could choose 2, 3, 4, or 5 different types. Now, what is the probability that you use carrots? So that's giving us our restriction. That's giving us our successful outcome, choosing carrots. So let's go through and break up our probability. NA divided by NS. Successful outcomes, total number of outcomes. So again, NS may be a little bit easier because again, we're looking at the total ways to do something without any restrictions. So what are we doing? Well, we're selecting vegetables. How many? We can select anywhere from 2 to 5, from 5 different options. So let's look at our first case. We could choose from 5 vegetables, we could choose 2. Or we could choose 3. Or we could choose 4. Or we could choose 5. So there's 4 different cases that we're going to be looking at. So we'll put that up here just so we keep a reminder. In this case, we do have to consider it for both. So there's 4 different cases. So 1 or 2, 3, 4, or 5 vegetables. So those are our different cases. So we've taken care of our total number of outcomes. So basically selecting 2 from 5, choosing 3 from 5, 4 from 5, 5 from 5. No restrictions. Doesn't matter what we're choosing as long as we're choosing a certain number of vegetables. And A, the successful outcomes. So we have to look at our different cases. So the case 1, looking at the 2 vegetables, if I choose 2 vegetables, one of them has to be carrots because again, the successful outcome is looking for carrots. So I have 1 carrot, choosing it, multiplied by 4 other options, choosing 1. Right, so that's 1 carrot and 1 no carrot. I'm not going to write that for everyone, but it is the same kind of concept. So the next one, the next case, I have 1 carrot, choosing 1 of it, times 4 remaining vegetables, choosing 2 of them, because I'm having 3 vegetables in this case. Plus 1 carrot, choosing 1, multiplied by 4 vegetables, choosing 3, plus 1 carrot, choosing 1, times 4 vegetables, choosing 4. So I'm looking at my, again, 2, 3, 4, or 5 vegetables being chosen. I can bring it all back together now. So I add up all the top. I end up with 15 ways over 26 total possible ways, which gives me 57.7%. So there's a 57.7% chance of choosing carrots or using carrots if I can choose anywhere between 2 to 5 vegetables to make this pasta sauce. So again, in this lesson, we are basically just adding in the idea of probability, looking at the total number of successful outcomes divided by the total number of possible outcomes. Again, we've just added in the idea that we can use combinations to help us figure out those different number of outcomes. Right? So using what we've learned about combinations, the different scenarios that we come across, Pascal's triangle, and just incorporating it into the probability formula. So if you're having difficulties with combinations, please make sure you go back and take a look at those on the previous lessons so you do have a better understanding of it. In terms of probability, you can go back to the previous unit entirely on probability to again look at the general format and how it's laid out.